Well, hi everybody. Welcome back. I appreciate that the lecture went on a little long this morning, but now we have the opportunity to talk about R. I realize that a lot of biologists have serious questions about why they should have to be programmers as well. And I was advised that it would be a really good idea to explain what R has to offer you. So without further ado, I want to proceed right into my answer to why you should bother learning R. The first thing I would say is that there's a world of code out there to help you do biostatistics and bioinformatics. R is not the only language that has benefited from them, but it is probably easily number 1 or 2. So I think that if you want to have access to many of the tools that make bioinformatics and biostatistics feasible, learning R is a very, very sensible option. If you are working with flow cytometry data and are generating FCS files, there's a library for talking to FCS files. If you want to manipulate a BAM file, you can do that in R. If you want to work with the metrics of a FASTA database, you can do that. There's a world of tools out there to help you do all kinds of complex challenges. It also has a very, very good support for what frequently gets called data cleaning, for lack of a better reason. A lot of the times you are receiving data that are not formatted consistently or in a structure that enables you to do good analysis on them. A lot of people think the answer is to open the data in Excel and muck with them until they're in the shape that they need to be in. But that tends to leave you with unspecified changes that have been made in ways that may have introduced errors of their own. Packages like tidyverse can go a really long way toward making your cleanup of data much more sensible, much more structured, and it's an excellent framework to learn to empower your later data analysis needs. You know, as you progress from graduate student, master's student to PhD student to postdoc to professor, I hate to break this news to you, but the problems you get called upon to solve get uglier and messier and more time consuming. So having some really good data cleaning skills that you learn as a graduate student can make your life a whole lot nicer when you are a senior lecturer or when you are an assistant professor or when you are a full professor, heaven help you. So I strongly recommend that you learn how to do good modeling, how to protect yourself and protect your students, for that matter, someday, against the false conclusions they may be fooled into if they use unstructured data analysis. R is a good place to protect yourself against those things. So if you are most people accustomed to using Excel for dealing with biological data? Is that what most people are doing? I've done a fair amount of that. One of the first papers I ever wrote was on the statistics of how peptides fragment, and I tried to do it all in Excel, and I have to say I ended up rewriting pretty much all of the data analysis in R because I had gotten myself into a place where the Excel spreadsheet could no longer deal with all of the complexities that I was trying to do. So that exercise reminded me how valuable it is to separate the data, the input tables, if you will, from the process you're using to yield biological information from it. If you can separate the program from the data on which it works, it becomes a whole lot easier for you to deal with a very common outcome. How many of us have had a professor come into our office and say, look, I know you've done a whole lot of analysis on this table that you started with 6 months ago, but we've produced a new one in the last month that's a whole lot better. Okay, that's not unheard of. This really happens. So if your script for dealing with the data is separate from the data themselves, that's an afternoon rather than a couple weeks. So I would like to save you some time, and I would like you to make it much easier for you to notice problems as well. You know, if you have to look at the formula for each step of the process to get from an input table to a biological conclusion, it's going to be a lot less clear to you where the bugs are or where you miscopied the formula. And there are a lot of ways that having your script for dealing with the data separate from the input table will protect you. And finally, I would note that we frequently need to write methods text many months after we do the analysis. If you're trying to reconstruct what you were thinking from a bunch of Excel formulas, or looking at a script that lays out what each step is, it's going to be a lot easier in the latter case to look at your R script and say, this is what I did in what order with these parameters. So you might think, okay, well, I know how to use Excel, I don't know how to use R. Why should I start learning something that looks on its face really complex? I would note that MS Excel is not, in fact, easier for all the things you want to do. So I ask if you've ever done a box plot in Excel. Has anyone tried that? Was it fun? It's not fun. Have you ever tried to do a histogram in Excel? Maybe if you have the wizard to help you, it's okay, but if you're entering an array formula for the first time and you have no idea that you have to hold down Control and Shift at the same time as you hit Enter to paste the formula across that array, I just gotta say, it's not fun. So I made a video about comparing the processes of making a box plot or a histogram, and you can find it at that YouTube playlist down there. I made a box plot and a histogram in Excel, and in GraphPad Prism, and in R to show how it compares. And I gotta say, Excel does not come off well in that comparison. I would also note that a lot of people enjoy GraphPad Prism. For some people, that's gonna be the best option. But it costs hundreds of dollars, and your ability to redo an analysis that you did in your former lab where they did have a license can be complicated by the fact that the new lab doesn't have one. Some professors, oddly enough, don't want to shell out hundreds of dollars to purchase a license to the software. R is free, and it's going to keep being free. It's been free since I was a grad student, and trust me, that was in the dark ages. Now, I would note that some people are really, really going to get a kick out of programming. You can't really know in advance if it's you or not, but for some people, it's just like you mean this was always available to me and I never knew that before? There's a language called Python that allows you a lot of access to similar kinds of libraries, and a lot of people in bioinformatics are preferring it as a relatively clean option versus something like Java or C++. I'm not doctrinaire about it. I've programmed in a lot of different languages over time. But Python is another language that can offer you a lot of this. But using it in R frequently gives you more direct access to the tools in biostatistics, particularly. Now, I feel that in science, we frequently act as though professors want all their students to become professors. But frankly, if you all become bioinformatics professors, I'm out of a job. So let me just note that you could go work somewhere else. But programming is a skill that is very, very transferable in the marketplace of industry. How many of the companies that might want to hire you care whether you know how to clone versus know that you know how to be a fourth industrial revolution data scientist? We have the option to learn all kinds of optional skills as graduate students, and there are very few that can increase your market value as an employee, or for that matter, as an entrepreneur in your own right, as becoming a data scientist. Data scientist is consistently in the top 10 roles that companies are trying to recruit, and they can't get enough candidates. So if you ever had a thought of leaving academia, being a data scientist is a very powerful entry card for a high-paying job. If you know how to use R, you are on route to becoming a data scientist. I'm not going to make you a data scientist in 5 days. Sorry, I'm not that good. But this is an entry point to that. Every laboratory, every business needs someone with solid numeracy skills. We spend a lot of time, talking about reading, writing, and arithmetic in education. Numeracy goes well beyond can you add, subtract, and do math on paper, right? Being able to wrestle big data sets and come away with a defensible answer about them is the name of the game for the 2020s. So I strongly urge you to go there. The other thing that I feel kind of doesn't get recognized is that we as scientists have always got to be disciplined about how we are going to go from data to conclusions. If you are a programmer, you are much more mindful of all the different things that go into the conclusions you draw from your data, and that is one of the #1 ways to protect you from reaching wrong conclusions from right data. Okay? So I would argue that we all need this kind of self-discipline to learn how to protect ourselves from wrong conclusions. Knowing even a bit of our programming will make you a better scientist. I feel very confident about that. If you get bitten by the bug, I think that you might decide this is a direction you want to go for your career and get paid a lot of money and have job security for the rest of your life. Just saying. I also note that occasionally, if people are very grateful and you work on their data sets, they may offer you middle authorship, which is good, but even better, they may bring you food. If you let it be known that you like jelly beans, for example, people may show up with jelly beans saying, I've got this one data set. So, free food. That's the other thing I hope to advertise. Okay, with that, yes, in my copious free time, I will analyze your data set. Or hand it to a grad student and still eat the jelly beans. No, that's unfair. That's unfair. All right. So again, this training is being supported hopefully by Diplomix, and I appreciate their consideration and watching this video. Let us then move to the day 1 script. I posted to the folder of our slides a whole bunch of R scripts, and this is the code that we're going to be working with today. This is a pretty simple demonstration, but I hope that it gets you started at understanding what kinds of abstractions, what kinds of tools basically are given to us by R for dealing with numbers. There are 5 of these little R scripts available in the directory where you downloaded these. They're in the same directory as the slides. I don't remember if I put the Why Bother Learning R slides in there. I hope I did, but if not, I'll add them. Okay. Now, you will probably be using RStudio. I'm going to use just R because I need to be able to have the fonts show up large enough that you can see them there. So if you're using RStudio and you have other windows there, those can help you organize, for example, data tables and scripts that belong to the same project. RStudio is a very valuable way to learn R, to support your learning R. I'm going to be just using the raw interface here instead. Okay. So let me return now to our script. You'll note that I've got a whole bunch of hash symbols here. These are not hashtags. These are comments, and in a lot of programming languages, we find that if you put a pound sign in front of the line, the software ignores it. Rather than just run this all as one big script, I'm actually going to walk through this bit by bit. So we note that variables are our friend from algebra. They're back, and very frequently, we can do bits of math that are very easy to understand. A equals 5, B equals 3. What do we notice happening here? Is R saying OK every time? It's not. Okay, so R is doing some stuff behind the scenes, but generally speaking, R is pretty quiet if it's accepting what you're telling it to do. What happens if I try something that doesn't have correct syntax? Maybe I say A is going to be the number 3.3. Well, we already see that the internationalization support is a little weird, right? So if I say A equals 3.3, it's absolutely fine. But if instead I ask it to use a comma as the separator, that's not going to be all right. So it may be that I've got my computer set to United States settings, so yours might behave differently. Okay, so generally speaking, you're going to get feedback from R if something is going wrong, but if it accepts that command and is not doing anything else, you're not going to get a warning to say, okay, I got that. Done, done, done. None of that. Okay, now I mentioned that we can do math. So if I remember that I've set A to 3.3, I've set B to 3. Here I'm using some shorthand again. I'm just typing the name of the variable and hitting enter, and it tells me what its current value is. So I can say things like C equals A plus B. Again, no response comes back from it. But if I say, show me the value of C, then it gives it to me. I could just tell it that I want to add the value of A to the value of B and not capture that. Right? So how does this line, C equals A plus B, differ from this line, A plus B? What we're using is something called the assignment operator. This is a big term for it. I mean, up here we said A equals 5, and I don't think anyone blinked. You understood that I was setting the value of A to 5. Here, I'm setting the value of C to whatever A's value currently is, plus whatever the value of B currently is, and I'm storing that result in C. I realize that if you've had any experience in programming, you may just take that all completely for granted. But if you've never done programming before, that can be very confusing. So I note that A plus B creates the value 6.3, but it's not captured to anything. It's just reported to the screen. Saying C equals that stores that result. Okay, we have several options here, right? So we've got A plus B, we have A minus B, we have A times B, we have A divided by B. That stuff is all there. All of that works just as you would expect it to. I already mentioned that you can type the variable name by itself and get its current value. But I would note that sometimes the math we're doing produces a result that's Boolean in nature. George Boole came up with this idea that you can do math not on numeric values, but on logical values, true and false. So we could say A equals true. We could also say B equals T. Now what have I done there? So I type A, I see its value is true. I type B, I see its value is also true. So the software is able to infer that just because I'm using T rather than true, it still knows that, oh, he's just using shorthand for true. Okay. There's a lot of things we can do with Boolean logic as well. So I've drawn a couple in there. I'm going to start with one of the most basic things. What if I want to know, is A the same thing as B? So there's a difference between equals and equals equals in R. So I'm going to try to illustrate that. So I can say A equals B. So with a pair of equals, it's asking a question. Are A and B equal in value? That is quite different than A equals B. You see that? One of those gave me the response true. The other one stored the current value of B in A. That's something that catches people out all the time. So remember that if you're asking the question, are A and B the same value, you want to use equals equals. And that works on numeric variables too. 4 equals 5? No. What about 4 equals 5? Ah, right. So you see, those are really different expressions. In the first case, 4 equals 5, we're asking a question. The software says, no, they're not the same thing. 4 equals 5 is attempting to set the number 4 equal to 5, which is not something you can do. You can't just reprogram a number's value in R. Okay. So we also have a couple things that you've probably seen in other forms. So if I said A and B and wrote out the word, it might seem very straightforward. So let me set I set A equal to true. I set B equal to false. I could just say T or F with a capital. Now, if I want, I can start by saying, is A the same value as B? That's not true, right? Because one is true and one is false. They're not the same. I can ask, what is the value of A and B? Now, do people remember their Boolean logic from high school? They cover it here? Okay. So here I'm asking, the only condition in which A and B is true is if both are true. So true and true is true. True or false, true and false, or false and true are not true, they're false. So here we say A and B, that's false, because A is true and B is false. They both have to be true for that to come through. So our math is getting a little further afield. We don't think about this all that commonly, but there are lots of cases in which we create logical values. So the pipe symbol is above your backslash on your keyboard, usually. A pipe B is to ask or. So true or false, false or true true or true. All of those give a true result. Okay, so we have lots of things we can do. But as I note down here, just because you're not using true and false as inputs doesn't mean you're not going to come up with a Boolean output. So let us try 5 is greater than 7. That's false. I can also do greater than or equal to 7. Now if I reverse that, 7 is greater than 5, that's true. 7 is greater than or equal to 5, also true. Okay, so you can compare numbers and come up with a Boolean result. Oh, I had one more I wanted to show you here. So 5 we said is equal to 5, right? So that's true. But there's a way to ask, is it something other than 5? That's the bang equals. A lot of times in a lot of computer languages, bang is the same thing as opposite of. Not is another way to say it. So 5 not equal to 5 is false. Okay. So we have covered a whole lot of ground already, but a lot of those things can trip people up, especially the difference between equals and equals equals. I would note that a lot of people in R also make use of the assignment operator spelled out a little differently. So previously I was saying A equals 5, which sets the value of A to 5. You could also say A gets 5. Oh, sorry, I botched something here. Oh, I haven't used that notation in a while, I'm sorry. That's the gets operator. So less than equals is a logical comparison. Is A less than or equal to 5? A with an arrow pointing in that direction, formed with a minus symbol rather than equal sign, that's the gets operator. So here I've told it A is now equal to 5. Some people will use those less than minus arrows to set a value in that way. So if you see that, don't be thrown off by it. There are a few cases in which the result of A equals 5 differs from saying A gets 5, but they're not really important differences for the purposes of this conversation. Okay, so let's now talk about data types. So it's nice to be able to set A equal to 5, but that's not going to be scalable to all the different kinds of mathematical challenges we want to take on. Do you guys remember matrix algebra? Ah, yes, I see you do. Yes. I might as well say, do you remember physical chemistry? Okay, right. So data types are what really let us move into an altogether more complex kind of operation in R. And a lot of times, this C function is something that we're going to use. Now, we've talked about operators, things like plus or equals or greater than or equal to. Those are operators. Now we're using a function. So I'm going to just run this first one here. I'm going to grab that guy out of there, copy here, and paste here. Boom. Okay. So when I type A by itself, I'm now going to see that I've produced a list. Technically, the name we're going to use here is a vector, but it's not hugely different here. So we have told R that A doesn't equal one value, it equals a whole list of values. Similarly, we're going to do the same with B. Now, I said this was a function, and I kind of assumed you all knew what that meant, but that's not really fair. A function usually takes on a form like, well, to use a more complex example, I could do something like our norm 1000. In this case, I have a function name, our norm, and I have parentheses. And inside those parentheses, I've put a bunch of parameters. So our norm is going to accept some parameter, and the parameter with a value of 1000, and that's going to affect what is returned from the function. In this case, it's going to be a vector of 1000 numbers, and I'm storing that in X. So there are several pieces here. The function name is specific to that function. You can't, it's a really bad idea, at least, to create a whole bunch of different functions that all have the same name. You can tell a function is being used by those round parentheses. You can see how that function is being configured, how it's being run by what parameters are passed to it, and there's a return value. Something is given back by that function that may then be captured. Okay, so the C function essentially creates a vector out of whatever it's receiving, and it passes that out, in this case to be captured as A, or in this case to be captured as B. So when we type A, we see those numbers. When we type B, we see those numbers. Okay, so in this case, I want to sum together all the A's and all the B's. So I'm going to say sums equal A plus B. Again, no feedback, because R has just simply said, oh, you want me to do that? I'm done already, right? So when we run sums, in my mind, the computer always speaks to me with attitude. Maybe your computer speaks to you more compliantly, but mine is always full of sass. I'm just saying. Okay, so here I had my A variable up here, my B variable here. Now I've told it to add it together. Now, what does it mean to add together one batch of numbers and another batch of numbers? It's kind of odd, isn't it? But in this case, R is using a fairly sensible attitude about the numbers you've given it. A had 5 numbers in it. 1, 2, 3, 4, 5. B had 5 numbers in it. 1, 2, 3, 4, 5. Therefore, sums is going to have 5 numbers in it. And 2 will be added to 21 to give us 23. 8 will be added to 7 to give us 15. 43 plus 9 is 52, etc. So you can see that already one command has led to many data being added together. This is kind of a parallel operation thing that's feasible in this context. You can even do this with things like matrices. Okay, so that's already pretty powerful. Now I want to show you an example where things are a little strange. I'm going to just grab this whole block of text out. Okay, so I started by setting A to these 6 numbers, and then I set B to those 2 numbers. But I did something funky here, because I added a set of 6 numbers to a set of 2 numbers. So what does alternating look like? Did R decide to add only the first 2 numbers on there? Instead, R took advantage of the fact that A had an even multiple of the number of items in B. B had 2 things in it, A had 6 numbers in it, therefore it alternated which of the B's was being added to the numbers. So 1 and 0 is 1, 2 and 1 is 3, 3 and 0 is 3, 4 and 1 are 5. Sneaky, huh? Okay, so if I have another number set here, 1, 2, 3, 4, 5, 6, 7, and now I add A plus C, what happens? Oh, now I get an error. So it was okay to add 2 vectors so long as one was a multiple of the other. But it's not okay to add 6 items to 7 items. The software doesn't know how to do that. Okay, so R is going to be logical, but it's also going to be logical in a way that may not be our logic. If you came to your average high schooler and gave them 6 numbers and 2 numbers and said add them together, how would they respond? Okay, R is always going to respond this way, but it's a little odd. It's not intuitive necessarily. Okay, so let me see. Now we have our sums vector here. That's all very good. We now want to do some interrogation of this. This structure is nice, right? It lets us do this multiple math thing. But I want to grab out individual numbers, so I'm going to use something called the index operator. That's something that we use with the square brackets. So sums 2. You see that? Now we've pulled out a number. Now that's kind of odd, isn't it? If I do, do you notice this big square brackets 1 in front of it? Is that what we did when we got numbers like if I were to say 15 plus 4, do I get back a 1? I do. Okay, so I'm getting effectively something back that looks like a list of one item. That's going to be important as we move ahead. So I can pull out individual items in that way. I could also pull out multiple items from sums. Oh, what did I do wrong? Yeah, I forgot my R syntax for a moment. There we go. All right, I'm going to try to unpack this. Sums has 5 numbers in it. We agree? 5 numbers up here. Sums item 2, sums indexed for number 2, gives us back just the 15. Everyone sees why it's the 15 that comes back and not the 52? So sums 1 would give us 23. Sums 3 would give us 52. Okay, that's good. However, this command failed. And that's because anytime you give R commands a series of numbers, they need to be assembled as a vector. So 2, 4 isn't meaningful to R. C of 2, 4, however, is a vector of 2 numbers. So if I give sums that vector of 2 numbers, then it returns the 2nd item and the 4th item in the list. Things got a little slippery, right? I mean, before we were just doing A plus B and everything was fine. Now we're having to learn stuff, I'm sorry. Yeah, so indexing is really important. It's very frequently the case that we want to pull out an individual item from a list or a few items from a list. And this index operator gives us the ability to do that. I really believe that people learn a lot from breaking things, so I'm going to do something weird here. I'm going to ask sums for the 7th item. But how many items are in sums? 1, 2, 3, 4, 5. We've got 5. What is that? Not applicable. Okay, so the software is not going to just crash. It didn't crash. It created a value, but that value was not applicable. What if I say, give me the 0th item of sums? That's a pretty cryptic response, isn't it? What it is saying is, I have a numeric variable, and its length is 0. It's saying empty set, if people remember set theory from math. Right, so the software has some weird responses along the way. If you ask it to give you the 7th item in a list of 5 things, it says that's not applicable. If you ask for the 0th item, it says I'm giving you 0 back. And not 0, but empty set back, actually. Okay, so we've done some funky things. You need to be aware of these things, because if you try to do coding and R gives you back weird responses, you might think, gosh, I'm never going to learn this. I would not want you to take that lesson away. Every programmer makes mistakes all the time. All the time. Programming is an act of making mistakes. It is the people who succeed as programmers say, gosh, I wonder where I fouled up, and start trying it step by step. Okay? Programming is not a natural activity for anybody. It's just that some of us take the time to say, well, gosh, I messed up. I'll find where I made my mess up. It's an important skill. So learning how to deal with these kind of errors is really, really important. So we're now going to use some operators and functions that give us ways to generate big lists of numbers. So we're going to just run through these bit by bit. I'm going to start with this little function call, sorry, not a function call. We're going to use an assignment. We're going to write a value to evens that's using a new operator for us. Have you seen the colon yet? I want to make a joke about colon cancer here, but I'm not going to do that. I'm sorry. I worked in colon cancer for 10 years, so sorry. Okay, so we're using the colon operator. The colon operator. If we use this is a complex command, so I'm going to break this down to just include that part, 1:20. You see how neat that was? So immediately we got back this range of numbers, all reported back to the command line. But we're going to do a programmer's trick to it. Remember, we're trying to create a vector of even numbers. So our programmer trick is going to be to multiply all of those values times 2. So you see how that worked. Originally, the series operator gave us the numbers from 1 to 20, but here we've doubled each of those numbers to give us from 2 to 40. So that's pretty cool. All right, so the series operator gave us the numbers 1 through 20. We multiplied those each by 2, and we stored that in evens. In this case, order of operations, I think we all might remember from high school classes, they still matter. So let us look at what happens if I say 2 times 1 colon 20. Still safe, right? But how is it different if we were to do, colon 20. You see how that's a different result? Right, so how we group things can matter. It's a good idea to use parentheses pretty liberally to remind yourself of what things are supposed to happen first. We want to create the numbers 1 to 20, and then and only then do we want to multiply them by 2. Okay, here we've used series by itself. Now I want to show you the rep function. How do I know it's a function? Because it's got the parentheses, right? Those round parentheses. Okay, so we're feeding the rep function NA, which I think we remember is not applicable, the value not applicable, and we're asking it to do 10. Now, how do I know that rep required these 2 arguments? I'm going to type question mark followed by rep. And we see that in my case the web browser has opened and it is showing me how does rep work. So you can see that it wants the values in x, and it needs to have, because I'm using integers, I'm going to give it the times argument as well. So whatever x was is going to get repeated times, if that makes sense. Do not be afraid to ask the software for help. There is a world of programmers out there. Yes, you can go to places like Stack Overflow and Google for the answer to your question. Programmers do this many times a day. Often, the manual can help us, and the manual pages, as you see, are just a click away. So that's good. So let us look at what resulted from our use of the rep function. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We asked it for 10 repeats of NA, and that's exactly what got stored in repeats. Which brings up the obvious question, what is Batman's favorite function in R? Yeah, okay. Doesn't get funnier on the 10th repeat, I gotta tell you. Okay, anyway, so here we go. Great, so we've got the repeats function right there. I do a lot of simulation of data sets for this little course. So in a lot of cases, I need to mock up some data that are very useful to us. So in this case, I want to launch the runIf command, function rather, with the value 100. See that? So randoms has now been populated with 100 numbers. That's what our runIf function did. So these are randomly sampled numbers drawn from the uniform distribution. Do people remember what a uniform distribution is? Some people do, some people don't. I often think of the uniform distribution as being a little like 100-sided dice. Have you guys ever played Dungeons and Dragons, for example? Oh, okay. Well, in my youth, I was known to carry a D20 with me. A D20 is a 20-sided icosahedral die. It's a big guy. You roll it and you get back a number between 1 and 20. And they were fair dice, meaning that each face had an equal probability of appearing. So if you rolled that die 1,000 times, you would expect to see roughly the same number of 1s as you did 2s, as you did 3s, all the way up to 20s. Okay, in this case, I'm not getting one of 20 values. I'm getting a number drawn from a continuous distribution across that. So I'll just note that every time I run this, I get a different set of numbers back. Now, how can I convince myself that where it lands on the number line is the same each time? First off, is there a range going on here? If I were to ask the help, you would see that I looked for the variable name rather than the function because I wasn't thinking. So now if I do the correct function, I should get my help open to tell me about the functions having to do with the uniform distribution. I used runif right here. And you see I specified a number of numbers that I wanted to come back. It's got a minimum and a maximum value, and these are defaults. So if you don't tell the software what the range of numbers is, it always gives you something between 0 and 1. Okay, so I can try to convince myself that these numbers really are. I'm going to show you a couple things that are jumping ahead a little bit. I'm going to use the histogram function on my randoms. Now, was that hard? No, you just said hist. Here's a variable, show me a plot. And the software made a whole bunch of intelligent judgments, assumptions about it, and said, well, here's what comes back. So every time I run this runif function, I'm going to get back a different set of numbers. If I did 1,000 numbers or 10,000 numbers, these values would probably be a little more uniform across here. But in this case, they come back pretty quickly. Okay, so already we've seen something that's kind of nice about this environment. You can very, very rapidly knock out a histogram. So, thumbs up. All right. So, let us now look at a few functions that come in handy for dealing with a long list of numbers. It's not always going to be sensible to spit it out to screen and try to gestalt something about those numbers. So we're going to start with wanting to compute the mean. So far, this is not different than what you would do in Excel, right? In Excel, you would write equals average this column, and then out pops your number. In this case, the string of numbers, or the vector of numbers, is all stored in randoms. We run the mean function on it, and back pops that number. Okay, now why is your number different than my number? If you just ran this on your laptop, you did not get 0.5433959. Each of our computers is running the uniform sampling differently. In fact, if I rerun my randoms here, oh, did you see what I did? I used my command history. So I hit the up arrow on my keyboard, and that let me move back to the most recent things I typed. Very, very frequently, even experienced programmers make typos. And sometimes it's useful to repeat the last command and go back and edit it. Very helpful. So the up arrow is your friend for that. So here I've rerun my runif command, and now I'm going to run means, and I see that instead of 0.543, I got back the number 0.561. Now I'm going to wager that most of us got a number back that's pretty close to 0.5. Why is that? Exactly. Yes, we told the computer, give us a number that appears somewhere between 0 and 1 that's uniformly distributed across that space. If you sum together 100 numbers like that, you're going to get something close to 0.5. Okay, so that's the mean function. And now we're going to do a summary on it. Now summary, I've got to say, is one of my favorite commands. Look how much information you get back in just one quick summary. Here I had a mean value. We got that just a moment ago, but it wasn't labeled quite that way. And now we have a 5-point summary of that. We have the minimum value seen, very close to 0. We have a maximum value seen, very close to 1. We have a median and a mean. Do people remember how median and mean differ? The middle value, exactly. Yeah, so the software has sorted our 100 values from lowest to highest, and it picked the one in the middle. But is there one in the middle when you have 100 numbers? There's not. There are 2 in the middle. So it's looked at the 49th and 50th. Hold on a second. No, I've got this backwards. It's looking at the 50th and the 51st values and averaging the 2. And so it's reporting a median from that. And we have a first quartile and a third quartile. So if you're trying to figure out what the interquartile range is for this, you can simply subtract the first quartile from the third. All very handy. Okay. You may have generated some pile of numbers and forgotten how many you had. The length function is there to bail you out. So sometimes you need to pull the length of a vector out. Length is there to help. So these functions are all very useful for vectors. All right, now I have just a few, oh my goodness, how much more do I have here? All right, I'm going to try to rocket through some of this, but it's important that we understand them. Factors are really, really valuable. I'm going to point out that we work with factors all the time, and we sometimes don't understand how much extra computation our brains are doing. When I look at the sign-in sheet, I see PhD, MSc, MSc, PhD, MSc, postdoc, 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 MSc, postdoc, PhD. That's pretty cool. I haven't given away personally identifying information on this video, so that's good. I would note that some people spelled out postdoc as two separate words. Some people put postdoc in one word. Some people put dots in PhD, and some people didn't. But my brain doesn't have to think about that. My brain looked at that and said, well, PhD is doctoral. This PhD is doctoral. If somebody wrote out Doctor of Philosophy, it codes it as PhD. You know, I don't have to think about it very much. If somebody had written Masters rather than MSc, I would have coded it as MSc in my head. So our brains are recognizing that people may write different things, and yet they all code to the same thing. And a factor is something very much like that. Imagine you're looking at biochemical data from a whole bunch of different animals, and you wrote down the sex of each animal as one of your columns. Now, maybe I'm gonna just tell a story about undergrads for a moment, and I don't mean to insult undergrads. They do a lot of hard work, right? Imagine that you, a graduate student, have subcontracted out the data collection on sex to some undergrad who is working in their off hours, right? So this undergrad has written M for some of the males and written male for some of the others, and in another case they wrote that little circle with the arrow pointing up on it. In a case like that, if you had coded all of that into a spreadsheet, you might have said, well, it doesn't matter, they must have always written M for male, or heaven help you, sometimes they wrote a 1 or a 0. I mean, just, people do stuff, right? Data collection is ugly. So it might be that when you look at those data together, you make the assumption that they always wrote M or F. Well, with a factor, we have the ability to do this in an orderly way. I have set up a vector called fruit. Oh, you thought we were going to do more numbers, right? We're not. We've shifted over to character strings. Okay, so I have created a vector of apple, apple, pear, banana, banana. And then I created another variable, this time siphoning it through the factor function. Did you see that? This is a constructor function. So we see that fruit and fruit F are different values. Fruit is a vector of apple, apple, pear, banana, banana. Fruit F is also apple, apple, pear, banana, banana, but you see that it's also written in here that it has different levels. And it doesn't have 5 levels, even though we fed it 5 values. It has only 3. That's because the factor function recognized that apple is used multiple times. Banana is used multiple times. And so it has created different levels to reflect that there are 3 distinct values of fruit. Okay, we remind ourselves that we can actually pull those out. You can ask it how many distinct values appeared here. Apple, banana, pear, all right there. Okay, now we can also use this to get straight to some math. So I'm going to imagine that we have one of these columns from a biochemical table. In this case, M and F were the only values that appeared, right? So I could say levels of this sex factor, and I get back F and M. Now, if you had an Excel column of sex, and you were trying to figure out how many different values appeared there, how would you do it? I'm going to wager there's a function that does it, but I don't know what it is off the top of my head. In R, that's pretty close. I mean, the factor data structure is designed to tell us how many distinct levels there are. So here I can check at a glance levels, sex factor, and determine whether male and female were spelled out at any point. They weren't. It's just M and F. So that's a helpful bit of a shortcut. But I want to note that we can even do visualizations of this very, very easily. I'm just going to use the default plot feature built into the factors data type. And boom, right away I've got my bar chart. So that's a pretty handy bit of shortcut for being able to characterize off the cuff whether the number of males and females is roughly equivalent here. We only had 6 people, right? I mean, that's not a huge distortion. But if you saw this big a disproportion when you'd done 1,000 people, you would be a little concerned about that. Okay. There are already too many males in science, we know that. Okay, so I mentioned matrices. People probably remember those with great fondness from earlier classes. I've personally found them a little stressful. So we have the 6 numbers, 1, 2, 3, 4, 5, 6. I've called a function, actually 2 different functions here. Remember we had the compose function to create a vector of those 6 numbers. There's the C right there. And we've passed that result to the matrix function to create a matrix. And I gave a couple named parameters here. I wanted to give it a value for by row to specify I want you to accept these values by row. I've told it to do that. And that the number of rows total should be 2. So what is the value that got stored in mat? You see that? That quickly we've created a matrix with the values 1 through 6 accepted by row in 2 rows. If I had changed this to by row equals false, the result changes, doesn't it? It's taking the data by column instead of by row. So how I set up these parameters affects which number goes in, whether rows and columns are transposed, essentially. Okay, so we're back to the way it was written in the sheet. So we've created a matrix that lets us do some tricks. Now this function, I think, is not a particularly easy one to follow, so I'm going to try to walk through it. So we've done a lot of bizarre things here. We've got some lists, we've got creates, and we have dim names. 3 different functions all in one command. So I want to point out that this is just row 1, row 2. That's a vector of 2 strings, basically. This is creating a vector of 3 strings. And we are passing that into a constructor for list. I'm going to try to show you what this part is exactly. So copy that. Okay. So in effect, we have 2 vectors of strings. One is going to give the row names. One is going to give the column names. And we're going to stick these together, not in one list, not end to end, but in 2 parallel lists that are stored in another list. And we can see that its value, the big list, what we've created is a list of lists, where the first item is the row names, the second item is the column names. And then we've fed that, we've assigned that to be the names of the matrix by this dim names function. It's not all going to be this weird, but occasionally R is going to require us to get a little weird. Okay, so we've now stored in the names, the names for our matrix, these col 1 through 3 and row 1 and 2. So you can see that up here, Matt didn't have names. It said I've got column 1, column 2, column 3, and I have row 1, row 2. But it didn't have names for them until we ran this dim names function on the mat object. So it counted on that matrix already existing But here it was just altering the names that were stored with that object. Some days this may make sense and some days it may not. On day one, it's kind of a tough ask, I think. All right. And I have to say that even though I'm a pretty experienced R programmer, I had to look up how to do that again to remind myself how these things work. It is okay to look things up and not to just know them off the cuff. Okay. I think people remember that when you have matrices, on occasion you want to flip them over. You want to do a transposition. So we are going to use the transpose function, which is so frequently used with matrices that it's just called T, to create tmat. So one of the effects of this was that it flipped it on its diagonal so that things that were columns originally are now rows. And things that were rows are now columns. And this wasn't a square matrix either. This was a rectangular one. We had 3 columns, 2 rows. Now we have 3 rows, 2 columns. So if you're going to deal with matrices of numbers, it's a whole lot better to be working in an environment that's designed for it than to be having to code this stuff up by hand. Imagine if you did this transposition by hand in Excel. Is it possible to transpose a matrix in Excel? It is. It's actually pretty easy to do, but a lot of people don't know that. The paste special command lets you transpose rows for columns as well. You can do these things in other environments too. All right. We can also do appending. So if I have my original... Oh, I think I botched something here. Oh, no, I did it. That's fine. That's fine. Okay, sorry. Lost track of where I was. Okay, so the I started with my matrix that had 3 columns and 2 rows before we did the transpose. I've now created another one called row 3, and I want to stick that onto, I want to glue that onto the larger matrix. Here I'm using the rbind function in order to stick row 3 onto the back end of the matrix we'd created. And as a result, bigger mat, the bigger matrix, now has a 3rd row added to it. Okay, so again, you can modify these objects after the fact. Okay, right. I added in some information there about distributions. I'm going to just sort of move through this part quickly, but we will end up using it later. Sometimes you want to sample from a uniform distribution, like the one that we were using earlier. Sometimes you want to grab numbers from a normal distribution. So there's a corresponding function like runif that works with normal distributions. Or you want to use a Poisson distribution, you can do that too. So in this case, if we had the uniform distribution, I could do a histogram of that very quickly. And that looks mostly uniform, I think. Oops. Gotta click on the title bar here. Okay. Sometimes we would want to look at normally distributed numbers instead. These are the ones that I sampled using rnorm above. And you can see that very quickly I've pulled out a bunch of a bell-shaped distribution of numbers. Again, very powerful to be able to do that in a hurry. You can do the same with Poisson distribution. And finally, I was going to show you, oh, I forgot about the data frame stuff too. I'm showing you those too. Frequently, we find that lists are used. Previously, we had the list of column names and list of row names that we passed in. This is also something that happens when we run statistical tests. So if we look at A, we have 10 numbers with a mean of 3. We have 10 numbers with a mean of 5. You can see that those were specified right here. And when we ran a t-test, we stored its result in another variable. But look at that. It's got quite a complex name to it. So C gives us a whole blob of text back. And that's because when we create when we run a t-test, it creates a list of things that knows how to print itself. So C has given us that back as a result. So type of C, it informs us that it's a list. We can even see that C has a structure to it. That's not very friendly looking, is it? What is it that people are looking for when they run a t-test? A p-value, yes. So here we see that if you just type the value of C, it tells you what the p-value is. It's right here. But if you wanted to grab that value out, you would want to know what the structure was of that blob that came back. And we see that p-value, p-dot value, is one of these things. So we could look at the specific p-value that's part of the list structure using the p-value field of it. Okay, so handy things in there. I realize that not all of this is going to stick on day one, and I'll try to take time to talk about how we're getting these values out as we move along. I have just one more thing that we really have to visit on day one, because this is Data Structures Day, and that would be data frames. Data frames should be written in capital letters when you deal with R, because one of the most common workflows in R is that you have a bunch of data in a text file and you're going to load it into R. The default way that it does that is to make a data frame from it. So I want to give you an example of what this looks like. First off, we created labels. You can see that I made 5 repeats of the word case, followed by 5 repeats of the word control. And then I created another variable called reading, and it was these 10 numbers. So you can see then that I'm trying to create the same number of labels that I have of data fields. And then I created a data frame using the data frame constructor function right here. And so if I run df, it's going to show me what was stored as a data frame in this. My labels all went into this column, and my readings all went into this column. So what we've done is to create what some might call a narrow data structure that represents these 10 readings, and they've all been named. Okay? So data frames show up all over the place in R, and I wanted to see that you were able to see that here. Why is this not a matrix? We did matrices, right? Matrices had rows and columns, so aren't they the same thing? And they're not. A matrix has the same kind of value in every row and every column, right? So when we had our matrix, the only kinds of values stored in here were all integers, or they were all numerics, to be a little broader. The data frame, that's not true though. We have one column that contains labels and one column that contains numbers. And that's quite different. I want to point out that summary still works on this. So if I run summary on df, you can see that it has 5 incidents of case and 5 incidents of control. What does that tell you about that column? Here I'm telling it, don't show me all of data frame. I want to see just the label field out of this. So it's going to grab that out, and you see something familiar here. Do you remember when we were making those factors out of male and female? Here, the software has automatically factored our column of 5 case values and 5 control values, and remembered that there are only 2 kinds of values here, cases and controls. So data frames are one of these things that do a lot of work for you. Here it is remembering, I'm going to do the summary again, that the reading column is a bunch of numeric values, and it can produce a nice summary for us of that. But it knows to treat these labels as a factor to keep separate these 2 different kinds, to keep clear that this is a factor in here. Okay, I'm not going to do more on this today, but you've already covered a lot of ground. You've seen that R can let you store individual numbers and variables. It's able to handle Booleans. It's able to handle character strings as well. Factors are an important data structure because they allow us to count how many times each of the distinct values can appear. Matrices are certainly feasible within R. If you need to go to even three-dimensional, for that matter, n-dimensional matrices, you can do that in R, which allows for an awful lot of interesting mathematical operations. Generally speaking, one of the most common workflows that we deal with is reading a text file, a text table into R, and doing some kind of modeling on it. Very frequently, that's going to lead us through the data frame structure. You've seen operators today, some that were familiar, like plus, some that were unfamiliar, like colon, for getting back a series of numbers. You've seen functions, lots of functions, everything from the compose function, C, to things like rnorm, which will give you back a distribution of random numbers from a normal distribution. There's a pile of functions out there. One of the things that we haven't hit today, but will in the course of the week, is the ability to use libraries. Libraries let people import a whole bunch of new functions that relate to a certain kind of operation. I mentioned flow cytometry data, for example. If you were going to work with flow cytometry data, R doesn't know what an FCS function is, our FCS file is. But the libraries that you can import for operation with flow cytometry do. So you can add new functionality to R just by loading these extra libraries into place. Okay, and with that, we're at the end of the lesson for today. I'm going to go ahead and kill the recording, and we'll go ahead and take some questions offline, okay?